Hello, everyone, and welcome to the seminar room at the National Maritime Museum, and welcome also to the final couple of hours of this Ice Worlds Festival, all about polar science and old and new technologies, and of course the very special chance to get a close-up view of the RRS Sir David Attenborough research vessel, which I'm told leaves at 8 a.m. Tomorrow morning, so do grab that opportunity to take a look at it if you haven't already. But for now, we've got our last talk of the day, our 4 p.m. slot, and this will be about understanding the Thwaites Glacier, popularly dubbed the Doomsday Glacier. So we're ending on a cheerful note. And so this talk will introduce the big questions that concern the fate of the glacier, which is about the size of Britain. What happens if it fully collapses? The International Thwaites Glacier collaboration has united researchers from across the world to gain an understanding of how this important glacier flows, fractures, and retreats. And with me here, I've got Anna Crawford, who is a researcher based at the University of St. Andrews, and who focuses on understanding the ins and outs of the glacier. So Anna, over to you.
Well, thanks so much, and thanks you all for joining me with the last talk of this great event. Yes, my name is Anna Crawford. I'm a postdoc at the University of St. Andrews, and I am specifically researching the Thwaites Glacier with this collaboration that's called the International Thwaites Glacier Collaboration. And I'm going to get into kind of why we're so interested in Thwaites Glacier itself and what this international collaboration is doing to learn more about it during the talk today. I'll first just really briefly introduce myself and my background. You can tell that I'm not from this side of the pond. I grew up in northern the US, did most of my education, my postgrad work in Canada, and I studied how massive icebergs in the Canadian Arctic deteriorated. So these are actually pictures of my work, oops, jumping ahead here, my work on these massive icebergs. You can see that they're the size of cities. They can be hundreds of square kilometers in size when they break off of the glaciers from where they originate in Greenland. But that was my past days of doing sexy field work, and now I'm behind a screen. So now I am part of the Thwaites Glacier collaboration, which I'll get into, and that has numerous field aspects of the work. But I'm behind the computer taking the data that my colleagues collect in the field and generating 3D models of glaciers, and then poking and prodding them in different ways to see how they will evolve in the future. So I want to introduce Antarctica a bit, if you haven't gotten enough of Antarctica already as you've been walking around. So Antarctica, is over the South Pole, and it is a sheet of ice that rests on land. And that's what we're seeing in the majority of this white area here. There's sea ice that surrounds the Antarctic continent. The sea ice is floating on top of the ocean. The ice that makes up the Antarctic ice sheet is resting on ground. And I'm going to be honing in today on this region. This is, oh, I keep pressing the wrong button. Let's see. Is that showing up for you? That's okay, I can point. Sorry, should have rehearsed this part. I'm going to point. This is the region of interest of the West Antarctic ice sheet. So this is a region that we're quite concerned about in terms of climate change and what could happen to the Antarctic ice sheet in the future. If the West Antarctic ice sheet is lost, that's about 3.3 meters of global sea level rise. We're not close to that yet, and we'll get into kind of more of the ins and outs of our concern about the West Antarctic ice sheet and its situation going forward. So to dive right into that, we have the West Antarctic ice sheet, and we see that it is thinning. So that's what these colors here are noting. And you can see those red areas are denoting a lot of ice loss and thinning of the glaciers in this region. And there's two glaciers that glaciologists have been focusing on for a number of decades. This Pine Island Glacier, and then its neighbor, Thwaites Glacier. And it's already been introduced that Thwaites Glacier is about the size of Britain. And if we were to lose Thwaites Glacier itself, that's about 65 centimeters of sea level rise. So we're quite concerned about this region since it's so massive, has such a potential to contribute to sea level rise. and is already kind of in retreat. Skip this slide. So already introduced Thwaites as being the size of Britain. I've introduced how much sea level rise could increase if we lost all of the ice that makes up Thwaites Glacier. It is currently contributing 4% of the current rate of global sea level rise of all the glaciers and inputs to sea level around the globe. This is Thwaites itself, so it's the whole basin that's denoted by the blue outline, denotes the edges of Thwaites, and it's kind of flowing into the ocean that's in front of it here to give you a bit of an orientation. So this is an animation to give you a bit more idea of the flow of this glacier. So glaciers flow, and then they also fail and fracture. So I hope you can kind of see here that the ice is flowing this way. It's also fracturing around here, so that's the icebergs that are detaching. And then you also are seeing a lot of movement in front here, and that's the sea ice that's in front of the glacier. And once in a while it breaks up, and you can see that a lot of movement of the glacier kind of is associated with that sea ice receding from the edges. And I just want to give you this animation to have it in your brain to see how Thwaites is kind of set up. So we have the ice moving from the interior of the continent to the ocean, and then we have ice actually flowing on top of the ocean at the edges here. So these are called ice shelves. They're part of the glacier. They're the part that extends out over the ocean. And I'm going to be referring to these quite a bit, in the talk today. So we have two different ice shelves at Thwaites. We have this one up here. It's called the Eastern Ice Shelf. We don't have anything else too creative to call it. This is fairly stable, or has been at least. And I'll get into some new results that are showing us that we're questioning this now. We also have the floating ice tongue, and it's another ice shelf. We're also calling it ice tongue. But you can see it's extremely fractured. And this is kind of it has retreated quite a bit, and it could be lost, going forward. So we've also been, we've already introduced that, this glacier has been dubbed the Doomsday Glacier. And I think I've already given some hints as to why, it's been given that name. So it's very large. It's the widest glacier on Earth with a width of 120 kilometers. We know that it flows very fast, and we know that that flow is accelerating. So you're bringing more ice from the interior of the Antarctic ice sheet and pushing it into the ocean. We know that it is thinning, and we know that parts of it are retreating inland. So it's big, it's flowing fast, and it's retreating already. And I'm going to get into this aspect a bit more on the next slide, but it's situated on a bed that slopes downwards as you go into the interior of the ice sheet. And this is a situation that makes it precarious to faster retreat in the future. And we're thinking about this glacier now because it's already retreating, but we're wondering if other glaciers that are in a similar situation as it could kind of retreat like that in the future. So we're using this as kind of a place to learn about processes that could impact glaciers elsewhere. I was talking about that reverse sloping bed, and I hope I'm able to explain these adequately for you. So this is the Antarctic without the ice. So if we were to remove the ice from this map, or from Antarctica, that's what this map would look like. And so we're really interested in this area here. You can see the dark blue colors there, and that means this region is well below sea level. And it's associated with very thick ice, and that's what those red lines there mean. So if we melt the edges that are in touch with the ocean, we're going to push ice into regions where the ground is deeper, farther below sea level, and there's greater ice, amounts of ice in terms of thickness there as well. And this is the situation that makes the glacier so vulnerable to really rapid retreat. And that's because if you start pushing the glacier down a bed that slopes downwards as you go up glacier, you can start exposing more and more of the ice face to warm ocean water. So that can start contributing to more and more melt and retreat. And then with that, you also have more ice reaching the ocean more quickly. So I should just note that that is one process that you might hear about in the news. It's called marine ice sheet instability. There's a second instability that we're worried about for Thwaites Glacier and other glaciers that are situated like it, and that's marine ice cliff instability. And it's something that I'm quite interested in. And you'll start seeing this animation play in a second here. It takes a bit to warm up. So if I was talking about those ice shelves that flow out over the ocean, if we lose those, we'll get to a situation like we see at time 3 here, where we have a vertical calving face. And if we continue to retreat over, again, that reverse sloping bed, we're going to get thicker and thicker calving faces. And at some point, the ice could fail on itself because there's so much strain associated with that tall calving face, and the ice can only hold itself up for so long. So I think we should see it fail here. And if it doesn't work, if it doesn't play in a second, I'll just move on. But I'll describe it while we're looking at it. So here we have the glacier. This is a simulation, obviously, of a very idealized glacier flowing from left to right. And we have the ocean surface noted right here. And I'm hoping that it's going to kind of go on us here. This is the ice cliff that I'm talking about. And this is the calving face that's underneath the water. And we're really worried about this part right here slumping and failing on itself. Let's see if lots of anticipation for this one. And I don't want to click it again because it might, there we go. So we saw that there was a bunch of stress that pushed the glacier basically to fail on itself here. And you can imagine if we now push this calving face into thicker and thicker regions, that process is going to happen more quickly. And that's this positive feedback process that we're worried about in this area. So I think I've probably given you enough cause to worry about Thwaites Glacier at this point. You know, it's big, it's retreating, it could retreat faster. So there's a number of us that are now looking and kind of collectively putting our interest and our work to understand Thwaites Glacier better. And that's the International Thwaites Glacier program. And we had one stand in the exhibit hall. We are made up of 8 different projects. And this is another just idealized version of Thwaites Glacier, where we have, again, the glacier flowing from here to the right. And you see that the different projects are named by these really well thought out acronyms like Time and Ghost, Dominoes and Melt and Tarzan. And we're looking at this glacier from all different angles. So we're looking at it from the sea, where we have a ship in front of the glacier, taking measurements of the sea from the seafloor, mapping the seafloor as well. We have teams that are actually on the ice, doing surveys, traveling around the ice, and also instrumenting the ice so that they can monitor it over the year. And then we also have teams like the one I'm on called Dominoes that sit behind that computer that I was showing on the very first slide, you know, doing the modeling. Again, using all of this amazing data that's coming to us from the field, making my models that much better. And I just want to note that all of our work, you know, is showing it's an example of kind of how a collaboration can be greater than the sum of its parts. You know, so all of our work is going to inform, in the end, policy and what you might have heard about the IPCC reports. That's kind of what we're all pushing towards. So we have these 8 different projects that are feeding different aims, but they're all kind of coming together in the end, working to give all of us as society a better idea of what's happening on the other side of the globe. And again, we're really looking at how much ice is going to be lost, how fast, and of course that accounts for how much sea level rise, you know, comes with that. So this is the most ambitious field program in Antarctica to date. We have, as I was mentioning, these 8 different projects working in Antarctica for over 5 years together. And it's funded through the US and the UK, and bringing scientists to this glacier from McMurdo Research Station, which is down in this area, and Rothera, which is up on the Antarctic Peninsula. And we're also bringing scientists there via ship, and we'll be doing more of that over the coming years. Our field operations were quite disrupted by COVID, as you can imagine, but we're getting going again this year. And this is just some of the examples, of the different marine infrastructure that are helping us to collect data in front of Thwaites. You have the Sir David Attenborough will be, ours soon enough. We also collect a vast amount of data from the air. The British Antarctic Survey flew some geophysical surveys a couple of years ago, which were particularly helpful for my work, giving us really great data from the seafloor in front of Thwaites and also the bed of Thwaites. So that really helps me build those 3D models to the best accuracy that I can. And then we have people working in the deep field, as I've mentioned. And I am not one of the people in the field, unfortunately, these days. But you can see that it can be a rather harsh environment. But we're also collecting this really important data. And because we're able to pool resources and personnel from both the US and the UK, it really enhances what we're able to do in the field. And just one more, because there's so many great pictures of doing field work. I had to put in 2 slides on this one. There is, I think it's quite amazing when we are able to get data from beneath the glacier. We have, in places, hundreds to thousands of meters of ice resting on top of the land. So you can imagine it's super difficult to understand what's happening underneath that, what that looks like, what the processes are there. So there can be a huge amount of energy put into sampling data, sampling underneath the ice. And what we do is use hot water to drill through the ice, deploy instruments, and collect samples, from that area. And that's a huge amount of energy and work, but it's really, really special data when we can collect it. And then, so we're talking about kind of, ships and aircraft and on ice work. Then we also have a number of different models. And this is where my work comes in. And I use a number of different models for a number of different reasons. So I'm just going to try to briefly explain them so I don't put you all to sleep about modeling. But I use 2 models, specifically called Elmer Ice and HIDEM. And I use 2 instead of 1 because, as I was describing earlier, ice flows and it fractures. And it's really hard to simulate both of those in a single model. So I use 2 different models that are specialized for each and pair them so I can see how the ice fractures after it flows. And my models, I guess I could have done a different orientation to show you, but they're in 3D. So, I can kind of simulate really detailed processes in 3D. But what I ultimately want to do is learn about these processes in a way that I can actually simplify the process. Think of just like a math equation. I might represent icebergs calving by an equation that can then be plugged into a much larger model. So some people are I'm interested in single glaciers. Other people are interested in all of Antarctica in one model. So I have to give them a really simple equation about how iceberg calving works so that it can be represented, in these large-scale Antarctic models. And an example of a larger model is called ISSM. And right here, it's not showing all of Antarctica, but it's showing its predictions of retreat, kind of where the blue lines kind of end for the area that Thwaites sits in. So I'm kind of nearing the end of the presentation, and with that, I get to show you some kind of highlights and new results from our international collaboration. So I was mentioning, that we have ships kind of operating off the near coast of Thwaites Glacier, and there was also this really impressive aerial campaign that took data above the glacier and above the ice shelves that extend out the ocean. And from that, we get these exciting new maps. And I don't know if they're exciting to you, but they're really exciting to me. So we have the extent of the ice shelves that I was talking about again here. And you can see, or you can get an idea of the really great data and maps that we now have of the seafloor in front of the glacier. And we also have, just to orient you, we have the two ice shelves here. This is a different orientation. And we have really great data now of the bed of the glacier just above, upstream of where it touches the ocean. And this is really important for my modeling work because the detailed shape of the bed directs where the retreat is going to go. So you had these troughs and ridges in the bed, and the retreat really follows those troughs. And then where it hits a ridge, it might pause. So the better we can know where those troughs and ridges are, the better we can predict where it's going to retreat into in the future. I think you should remember, yeah, so if we can remember this ice shelf, and as I was describing earlier on in the presentation, we think that we were considering that to be the more stable of the two ice shelves, but we're learning more about it through the models that I was describing. And so now we have the glacier kind of flowing from the top right to the bottom left. This is the ice shelf and it's over ocean. And I'm just going to show you how my model simulates its breakup. And what we see is a major fracture happening diagonally across of it, and then a major iceberg here. And what we're really worried about is how this will progress and potentially lose the ice shelf. And this is all happening because this part is over ocean, but there's a small amount of the ice that's resting on a high point of the seafloor, and the ice is basically compressing itself. And because it's pretty weak ice, it's able to fail in this manner. So those are, and finally, there's, going back to my work on marine ice cliff instability, it doesn't look like Thwaites, but it's a very idealized block of ice. And I'm using it to study the process of marine ice cliff instability. And this is the one where the height of the ice cliff actually caused the glacier to collapse on itself. So you're seeing that there's a big slumping here, and then the rest of the glacier will fail buoyantly because it will no longer be in an equilibrium state. So I've kind of given you a crash course on Thwaites Glacier and all these new results that we're getting out of our work with the International Thwaites Glacier collaboration. And of course, there's further work to be done. A lot of it has to do with understanding now that we have a good understanding of the processes contributing to Thwaites Glacier's current retreat, how does that look in the future? How does Thwaites Glacier evolve as we move forward in the era of climate change? And I just want to highlight that the International Thwaites Glacier Collaboration's field teams are going into the field now. So over the next few months, you might hear about Thwaites Glacier in the news. There's usually some media attention, as the field teams are out there and as they come back. So look out for that. There usually is some press releases when we publish new science. So you might hear about Thwaites Glacier work that way. And I hope that there will be kind of more media and more outreach events such as what's been going on here over the years to come. So thanks so much for listening to all that. There's a lot covered there, and I'll take any questions that you might have.
Thank you, Anna. That was absolutely fascinating. And I'm aware I said a bit facetiously at the onset that we'll end on a cheerful note with a name like Doomsday Glacier, but I actually think we have. So thank you. I'm going to field questions. So raise your hand, and if you can state your question loudly, then I'll speak the question into the microphone. Young lady at the back here.
Obviously, there's a lot to be concerned about. Is there anything to be optimistic about?
Yeah, absolutely.
So the question is, there's a lot to be pessimistic about. Where can we find optimism?
Yeah, I think, to start on the pessimistic side again, by prompts, I'll turn it around. We are retreating, and we've changed climate enough that we'll inherit some glacier retreat and sea level rise. But what our actions look like now will tell us what kind of retreat we get more in the future of. So if we can curb our emissions, there is a good chance that we don't raise sea level rise by that much. Is that? I'm not saying that so eloquently, but our actions today do influence what's to come. We can still change the course of where we're going. So that's really important. And I didn't go into all the different processes at the glacier, and I was talking about instabilities and how this could accelerate upon itself. The retreat could accelerate. There's a lot of questions. There's lots of uncertainties there. So we're still teasing apart to find out if those instabilities are actually going to initiate or not. And there's different ways that the glacier could actually kind of slow itself down as well. So, but I think we need just to, keep focus on our action. Our actions that we take are influential going forward.
Any more questions? We've got one here from a young lady.
Thank you. That's great. Thanks a lot.
No, thanks.
What do you think we need to do to get politicians to take account of this? I mean, do you think the media teams of these projects should be funded? Really well, because getting the message out is really crucial.
Great question. Basically, the interfacing between cold hard science and the decision makers.
I think that the more media coverage we can get, absolutely, but also the more public interest in events like this, all pushes towards politicians being given that social license to act. So I think that's another way that we can influence things. Is because we can change individually, but we also need more systematic changes. So I see kind of a loop happening where our science and people's interest in it, and concern about the issues drives the politicians to act, and then the politicians hopefully driving us to be, and systems in general to change more quickly.
Who else wants to ask a question? Got one here from a young lady at the front.
If, you mentioned all the different projects.
Yep.
Are there any elements of the ice sheets you haven't been able to look at yet, or things you discovered along the way that if you got more funding to do more, what would you do next?
So
The priorities to look at.
if your research had more money, more funding, where would what would you look at next?
Yeah. I guess can answer that for my personal project best. My project. I said it was a 5-year project overall, but the Dominoes one is actually only 3 years, which is a bit sad. And we're just discovering about these instability processes and what they're going to look like. And I could surely use more time to look into how Thwaites itself, like the if and when those instability processes initiate. So that's kind of one thing on my end that I would like more time for.
Question from a gentleman at the back here. So I guess it's a question about international buy-in, not just UK and US.
And yeah, it's nice that you gave me this opportunity to also highlight some other partners.
Sure.
So we do have interest and investment by teams in Korea as well as Sweden, and likely elsewhere, kind of projects where people are involved from outside the US and the UK. And absolutely, I guess I'm going to go back to that question about influencing politicians. And I'm not sure about interacting with those large, heavily polluting countries or emitting countries specifically, but I think it's getting the other large and powerful governments to influence them. That's how I would. Yeah, that's my opinion. That's hard science.
Right, another question from a gentleman way at the back here.
Regardless of just the UK's involvement. And I don't think it's the politicians. I think it's more to do with the energy companies themselves and the politicians facilitating them.
Multifaceted question. Did you hear it, Anna?
I did hear it. Thank you.
So I think we know who the big polluters in terms. We know which countries pollute. Effectively, how can we think both commercially and world leaders? How can we get them to understand the gravity and to take action?
I guess in terms of what we can do as scientists is get the word out there about the results, and work with our partners. For example, at the British Antarctic Survey, have an excellent communications team that help us reach a wide number of people. And I think that we are making inroads in terms of showcasing the importance of Thwaites Glacier and Antarctica. And I think it's convincing, these large governments, research programs run by, that are funded by the government to increasingly fund this work. I would say we're a relatively small community that study Antarctica for the significance of its retreat on global society. So I do think that there's more investment needed, by those into these really important programs. So I would say, hopefully we can continue to convince those that this work needs significant funding and further collaborations, because this one will end in a few years.
To what extent will your research feature in COP26?
My research personally kind of works into those sea level rise projections, that are out there, and specifically like the International Governmental Panel on Climate Change projections of sea level rise. So I can only assume that the politicians are well aware of those different curves, on the sea level rise graphs. So that's where my work specifically works in. Lots of others involved with Thwaites Glacier collaboration, as well as Antarctic research and the Southern Ocean, are at COP. There's a pavilion just on the cryosphere, and there's others on the oceans, giving talks on the importance of this work, hoping to get the ear of different people that are involved, in the different negotiations that are ongoing.
Let's grab one or two more questions. We're running out of time, but this is very interesting. So, a gentleman here at the front.
Do those hot water drillings
Yeah.
that you mentioned, do they contribute to ice fractures? And have you modeled that?
The hot water drilling, do they contribute to fractures in the ice?
Yeah, I've never heard of a hot water drill hole contributing to a large scale fracture event. I think the scale of the extent of the ice and its thickness means that a local drill point isn't going to cause a large fracture elsewhere. Yeah.
How hot's the water? Just as hot as possible.
There's someone in the back that might know how hot the water is.
Just below boiling. Thank you. One more question, one final poignant question to close this series of talks. Who wants to take it? Maybe one of our younger audience. Ask a tough one.
Oh,
No? Oh.
Right.
Ah, sorry, beg your pardon. Yeah, lady at the front. It's a great question. How do you validate the models?
Yeah, absolutely. That's
Thank you.
extremely important part of the whole process. For my personal modeling, I actually have validated my models on how glaciers evolve in Greenland. So there's some retreat happening there that I'm able to replicate in my model. And that's my validation. But the large scale continental scale models that model the retreat of all of Antarctica, they actually go way back in time to show that they can simulate sea level rise over millennia. And that's largely how the validation works on the larger scale.
And with that, Anna Crawford from the University of St. Andrews, thank you very much indeed. And thank you to the audience.
Thank you so much.